Hi viewers, welcome to all. Here we are discussing about a project variable precision approximate floating point multiplier for efficient deep learning computation. A variable precision floating point multiplier is suggested for use in the short article with the purpose of making deep learning computations and more energy efficient. Okay, this architecture that has been proposed offers support for approximation multiplications using bfloat 16 format. In deep learning models, the input and output activations often follow a normal distribution. This distribution is inspired by the posit format. For number of varying values, different precision may be used to represent them. In this architectures that was present, the changing the amount of approximations is accomplished by the use of posit encoding, and the value of the product exponent is what determine the level of accuracy achieved by the calculations. In the case of a big exponent, and the mantissa is subjected to the multiplications with a lower accuracy, but in the case of the small exponent and calculations is subjected to the greater precision. A proposed design makes use of truncations as an approximation approach with the number of bit locations that are going to be truncated being determined at the value of the product exponent. To reduce the logic sizes in the variable precision floating point multiplier, here the proposed architecture presents the area and delay and power efficient XOR mux modified booth encoding method with a velocity adder in will reduce the number of logic gates in the precision floating point multiplier. Finally, this work was developed in Verilog HDLs and synthesized on Xilinx Vertex 5 FPGA and compared all the parameters in terms of area, delay and power. Now we can verify the base paper. So this base paper we have focused for the floating point multiplication. Okay, so here the floating point multiplier means we have different types. First one is a single precision, and another one is a double precision, multi precision and variable precision. This one is a variable precision. So if you are checked with a single precision, this is the architecture. So even these architectures and variable precision architectures, all the architectures will be same. Okay, so here floating point multiplier means it's a floating numbers based multiplications. For this floating numbers, we have differentiate this from the normal multipliers. Example, this multipliers we need to split with exponent, sign bit and mantissa. Okay, so here you can verify the architecture. The sign bit will be XOR and the exponent will be added with subtracted with the bias input. Okay, and mantissa will be multiplied, finally come up with normalizer and multiplication result. Okay, so here the same architectures only they are given. Okay, but the precision concept they are added here. Okay, so here also we are given as a input and B input. It will come up with the input processing. After that we need to split the sign bit and exponent. Okay, so here the sign input we need to split, and exponent input we are given into the sign and the exponent processing. Okay, so here this is a precision control block. Okay, so we need to increase more accuracy in the mantissa multiplications. For this precision will be helpful for that. Okay, and this is a mantissa multiplications input. Okay, this precision control will helpful for to high accuracy in the product output, and this precision output we are given into the mantissa multiplier. Okay, after this mantissa multiplier we are given the data to carry propagator and come up with normalizer and expression handling. Okay, finally the product output here. Figure 3 shows the proposed approximate mantissa multiplier. So here they are used the booth algorithm, radix 4 modified booth algorithm based mantissa multiplier they are used. Okay, so here we are proposed with this booth algorithm into this MBE multiplier. Okay, so modified booth encoding method. Okay, so this is different with the normal booth multiplication algorithms. Okay, so here we are generated this booth multiplier as per this architectures. Okay, so initially we need to loaded the multiplier and multiplicand value into the booth encoding logic. After that we are generated the partial product generation and accumulations with the velocity additions, finally come up with the carry propagation adder. Okay, and the proposed method also designed with the conventional full adder and also for XOR mux full adder. Okay, and this work also designed with the truncated part. Okay, so here truncated path will be scheduled with the mask output. Okay, so here this precision control output given to the mantissa multiplier, right? That mask output will be used for the multiplier truncations. Okay, so here you can check the figure 3a and figure 3b. Okay, so here the mask will be all ones. Okay, so it's totally 11 bit. So all the 11 bit will be high, means the mask we are not mask the multiplications output. So if the mask will be present 1 2 3 4 bit will be 1, means okay, we are mask the balance LSB bit. Okay, so here all the zeros will be masked. Okay, only 1 bit only we are taken as a final output. Okay, so based upon this truncations we are added a precisions in the mantissa multiplication final output. Okay, so here we are developed this work in Verilog HTLs. So this is a Verilog HTL test bench verifications coding. So here we are generated a 3 level of input architectures. Okay, so this is the first one, second one, third one. So here we are given input A and B and output. Okay, so this is the expectations results. Okay, so here this is a binary configurations, we are loaded this. Okay, so here this is a top model of the code. Okay, so here we are given the sign exp processing and precision controller, MBE multiplier, carry propagated, everything given normally. Okay, and this simulation output will be taken here in the modelism software. Okay, you can check the simulation for first output, second output and third output. Okay, so using this website we can check the floating point numbers. Okay, so input versus output. Okay, and this part we have synthesized with the 2 different architectures. One is for conventional full adder, another one is for XOR-mux full adder. So this is for conventional full adder synthesis report. Okay, so here you can check number of LUTs and number of occupied slices, number of IO bits. Okay, and the synthesis report you can check delay. Okay, 21.481 nanosecond and RTL schematic. Okay, so this is the RTL schematic for the conventional method. Okay, and this is a proposed method. Okay, so here you can check number of LUTs and number of occupied slices, IO base. Okay, and synthesis part you can check delay 10.188 nanosecond. Okay, and you can check the RTL schematic. Okay, so here RTL schematic you can check the inputs and outputs of all the configurations. Here we are given A input and B input. It will be given directly to the MBE multiplier. Okay, and okay, and it will be splitted into the sign exp configuration. Okay, so this sign exp configurations will provide the exponent output. Okay, so it will given into the normalizer and precision controller. So this is a precision controller and gate logic architecture. Okay, and this is a carry propagate adder, and this is an MBE multiplier. So MBE multiplier designed with both encoding logic. Okay, and partial product generator. Okay, so this partial product generator output given to the Wallace tree addition. Okay, so this Wallace tree addition designed with exact compressor. Okay, 4:2 compressor with the full adders. Okay, everything. So this exact compressor also designed with XOR-mux full adder. Okay, so this is XOR-mux full adder internal architecture, 2 XOR gate and 1 multiplexer. Okay, here we are updated all the comparisons parameters in the table. Okay, here you can check the comparisons table, existing versus proposed. Okay, and we have written abstract document for this project. Okay, so here you can check the abstract document. So base paper abstract, improvement of the project, proposed title, proposed abstract, existing system. Okay, disadvantages and proposed systems. Okay, and related notes. Finally, literature survey and references. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.